Hi everyone, today we'll continue our discussion on voltage sags and interruptions, and we'll go over some mitigation techniques. Just to recap, voltage sag is when the voltage magnitude drops below 0.9 per unit, above 0.1 per unit. Depending on the duration of the event, we call it either instantaneous sag, momentary sag, or temporary sag. On the other hand, if the voltage magnitude goes below 0.1 per unit, below 10% of the rated value, then this event is known as interruption. There are a variety of techniques to help either prevent sags and interruptions to take place or to lessen their impact and severity on the equipment and the grid. And this is the focus of our lecture today. To mitigate voltage sags and interruptions, we can either focus on the root cause of the event, which would be the short circuits, on the power system, or on the load side. Short circuits, of course, you remember, these are not the only root causes of voltage sags, but are one of the main ones. So our focus could be to try to figure out how we can reduce the number of these events. When it comes to power systems, our focus would be to make the protection system more efficient and faster, apply redundant designs to, for example, reduce the impact of these faults on the equipment. So these are some of the techniques that we can adopt. On the load side, either we can focus on the equipment itself, try to make it less vulnerable to reduction in voltage, or we can add auxiliary devices and components at the interface between the component and the grid. These are equipment that would help the appliance withstand reduction in voltage for a longer period of time. So these are the different areas that we can focus on, and this is what we're going to be talking about for the rest of this lecture. All right, let's focus on the ways we can reduce the number of faults. There are a variety of different techniques we can use, some of which I have listed here. One is to use underground cables. Underground cables are less prone to short circuit faults compared to overhead lines because they are more protected and they are not affected by weather events or tree branches or animals or things like that. You do, however, need to keep in mind that if there is a fault in underground cables, most likely it would be a permanent one, unlike overhead lines that in a lot of cases, these are just transient and temporary faults and they move away after a while. Another technique would be tree trimming. Tree trimming is important because a lot of times when you have an overhead conductor and current passes through it, because of the ohmic losses, the conductor elongates a little and sags. And as it sags, it's likely to get closer to tree branches that are growing in the vicinity of the line. If the distance is smaller than a certain threshold, a flashover might occur between the line and the tree branch, leading to some sort of a short circuit. So one of the things that people do, especially in forested area, is that they trim the tree branches on a regular basis, which is quite effective in reducing the number of faults. Of course, we have to keep in mind that it has some negative environmental impacts. Another approach which can be adopted in forested areas is to use tree wires. So overhead lines in general are bare conductors. They don't have an insulator around them. But in areas that you're prone to have a lot of tree branches and tree trimming either is not practical or is not cost effective, one option is to use tree wires that have insulations. When you have insulations, that means you wouldn't be worried about, for example, the conductor getting close to a tree branch or even making contact with one. So that's another technique that people use in forested areas. In areas that we have a lot of contamination in the air, either smog or, for example, in coastal areas, one of the things that utilities do is they wash insulators on a regular basis. When contaminants kind of collect on the surface of the insulator, they can reduce the effective dielectric strength. So that means that for lower voltages or lower distances, you might have a flashover and a short circuit. Another technique which is very common in areas where the distribution system is prone to a lot of lightning activity, we can use shield wires. This is typically very common in the transmission system, using shield wires on top of the transmission tower. Not so common in the distribution system. However, as I mentioned, if lightning is a major concern in that area, that's one of the things you can do to reduce the number of faults. And what these shield wires do is they provide sort of a point of attraction for the lightning. So the lightning, instead of hitting one of the conductors, it will hit the shield wire, or guard wire, another name for it, and then it would be diverted into the ground, so basically bypassing the conductors. Surge arresters are another type of device that are used for exactly that. What they do is, again, they capture the transient that is moving along the conductor and then divert it into ground. This is something that we'll talk about later when we discuss transients, switching transients, and lightning transients in particular. Both these solution techniques, what they do is they divert, for example, lightning energy into ground. So that means that the grounding of the poles are extremely important. If you have a low impedance grounding system, what happens is this energy will be quickly dissipated into ground, which is exactly what you want. So improving the grounding of the poles is another mitigation technique that utilities adopt. There are other things that utilities can do. For example, they can increase the spacing between the conductors. That is in particular effective if your area is prone to high winds, meaning that the conductors might move around and gallop, so to speak, and as a result of that, they might actually get close to one another. And if they do, chances of flashover would increase. By increasing the distance between these conductors, you can avoid that situation. Again, in areas which are forested with a lot of animals, using animal guards is one thing that can help prevent animals climbing up the poles and getting close to the conductors. Or, for example, having these sharp metals on top of the poles to prevent birds, nesting or sitting on the pole. So these are some of the things we can do. And of course, finally, you can increase the insulation levels to make it a little bit more conservative. And this, again, helps reduce the number of short circuits. All right, imagine we can do all we could by reducing the number of short circuits that happen in the system. However, we can never reduce that number to zero. So you will always have some faults and disturbances in the system. So the next approach for us would be to shift our focus to the power grid itself and see what we can do to reinforce the grid against these types of events. One category of things we can do would be to improve the protection system. Here, of course, you have to keep in mind that designing the protection system to mitigate voltage sags would be different from designing the protection system to mitigate interruptions, because we have different objectives. When it comes to voltage sags, our objective is to clear the fault as soon as possible, just to make sure that less number of customers would actually be experiencing that reduction in voltage. So this means that on laterals in particular, you're going to have to use fast fuses so that they operate before the circuit breaker at the substation or the recloser would operate. So you want to isolate that faulty lateral before everybody on the circuit, on the feeder, would experience that reduction in voltage. Another thing we can do is we can make the backup protection faster. Now, this is not going to specifically help with the initial fault, but if your primary protection system does not kick in for whatever reason, then instead of waiting for a longer period of time to backup protection kicks in, your backup is going to be faster, again, meaning that the duration of that voltage sag event for the customers would be dramatically reduced. One other technique that we can adopt is usage of current limiting fuses as opposed to expulsion fuses. These are specific fuses that have two characteristics. One is that they force the current to zero before it naturally occurs. So typically what happens is when you have a fault current and if you want to open your contact, you would have to wait for the zero crossing of the current. And remember, this is a sinusoidal waveform. These current limiting fuses, what they do is they actually force that current goes to zero before that, half a cycle passes. So they provide a faster response. In addition to that, they have a benefit of being able to limit the magnitude of fault current. So this way, in terms of voltage sags, the benefit would be twofold. The duration of the event would be less, and the dip, the amount of dip in the voltage that we get, would be less. So this is if we want to improve the situation related to voltage sags. How about interruptions? So for interruptions, our objective would be different. Unlike voltage sags, which we would like to clear the faults as soon as possible so less number of customers would experience that reduction in voltage, for interruptions, we would actually want to avoid actions that lead to interruption. So in this situation, we would actually be okay with a larger number of customers experiencing a voltage sag as opposed to some group of customers all of a sudden losing their service. And again, if you remember from our discussions in class, this technique is typically effective in situations where majority of faults are transient in nature. One technique that we have discussed in class is the usage of auto reclosers, and have auto reclosers respond to the fault before the fuses on the laterals try to interrupt the fault. So this way, before the fuses have an opportunity to melt, which is going to be like a permanent interruption, and the utility crew have to drive down the feeder to find that fuse and replace the fuse element, here the auto recloser will have multiple reclose operations to try to see if the fault is transient in nature. So this will avoid the number of large-scale interruptions that people will have. If you don't have a recloser, you have to make sure that your fuse relay coordination is optimal, meaning that you have to make sure that the devices respond to the event that would lead to least number of interruptions in the system. And of course, another technique would be to filter the third harmonic components in the system. And this is because, as you recall, third harmonic components are basically zero sequence. That means they add together. So they typically flow into the neutral of some devices. So some of the ground fault relays that we have, they sense the neutral current, and when they sense a non-zero current in the neutral, they basically assume that there has been a fault and disconnect that circuit. So third harmonic components, despite the fact that they have nothing to do with the fault, they're just a natural characteristics of certain types of loads, they will trick the relay into thinking a fault has occurred. So if you have ground fault relays, one thing you can do is you can filter those third harmonic components so they don't flow into the neutral system. All right, so here now we have an activity, and I kind of want to put the things we discussed in the previous couple of slides into practice and see if we feel comfortable with these notions. So here I have a power distribution system, and I'm assuming that I have inverse time characteristics for all the protective devices. Relays, auto reclosers, fuses, everything. How would you coordinate the protective devices under the following conditions? First scenario is you have a system that is predominantly consisting of overhead lines running through a forested area. Second scenario, you have a system consisting of a main feeder which is highly reliable and has laterals that are predominantly underground cable. And last scenario, we have a system which is located in a geographical area prone to extreme weather conditions, storms that are very common. So at this point, what I would like to ask you to do is I would like you to pause the video, give yourself 5 or 10 minutes, think about these scenarios. When you're ready, hit play to go through the solutions. Okay, I'm assuming you thought a little bit about this problem. Let's go through the first scenario. We have a system that is predominantly consisting of overhead lines running through a forested area. In a situation like that, we can imagine that majority of faults are temporary. If faults are temporary, we would like to save our fuses. So we don't want them to trip on these faults because that would lead to permanent interruptions for customers. So instead, we will use an auto recloser that would be set to respond to faults before the fuses do. And even to make things more effective, you can use multiple strikes. So you open the recloser and then close after a couple of cycles to see if the fault is there. If it's still there, you open again and you wait for another dead time. You do multiple strikes until, for example, the fault is removed. As you can imagine, the second scenario is the opposite of that. If you have a high reliability feeder and laterals that are underground cable, this means that majority of faults are going to be permanent. In this case, there is really not much benefit in using auto recloser because you're just going to be reclosing multiple times into a fault. Not only it's not going to avoid the eventual interruption that you need to have, another problem is you're going to have transients as a result of closing into a fault. As a result, in a situation like that, you will actually want your fuses to respond to faults before the auto recloser or the main circuit breaker at the substation does. So this is going to be opposite of the fuse saving approach. And lastly, what if a system is in an area in which storms are very common? So this is somewhere in between, because during the storm, the faults are mostly going to be transient and temporary in nature. However, during normal operating condition, when the weather is okay and there is no extreme weather conditions, chances are that faults are not temporary. In a situation like that, what we can do is we can have an adaptive coordination scheme, in a sense that when there is storm, in order to be proactively prepared for it, you revert all your auto reclosers to fast tripping mode, meaning that they will be starting to respond to faults before the fuses do. This way you will be saving your fuses. However, when you go back to normal conditions, you just change the settings back to what they were, meaning that the fuses will be the ones responding to lateral faults before the substation breaker. Okay, in addition to improving the protection system, when it comes to the power grid itself, one other thing we can do is we can reduce the severity of faults. So imagine we have done everything we could about reducing the number of these faults. We have done our best to have a very efficient protection system, but this is not enough. Other things we can do is to help the system maintain its voltage for a longer period of time. One approach would be, for instance, to install distributed generation units. What these units do, especially if they are located next to sensitive loads, is they can help provide voltage for a longer period of time, meaning that the sensitive load is going to be able to withstand that reduction in voltage for longer periods and can tolerate more significant voltage sags compared to the case when there is no distributed generator. From a system capacity perspective, essentially adding a DG unit is similar to increasing the short circuit ratio of the system, making it a more stiff network. Another solution would be to feed sensitive loads from multiple substations, so that if, for example, through one path the load is experiencing dip in voltage because of proximity to a short circuit, for example, from the other path, from the path of the second substation, it still has access to rated voltage. These two substations basically work together to make sure that the overall voltage at the sensitive load location is going to be higher. Of course, keep in mind, in order for this technique to be efficient, these two substations have to be independent of one another. And of course, one other thing that we can do is we can use inductors in series with the lines. These are current limiting coils that basically what they do is they try to limit the fault current. Mathematically speaking, it's like it increases the electrical distance between your load location and the fault by increasing the impedance between load location and the fault. This, of course, is efficient for a lot of sensitive loads, but keep in mind that it could make voltage sag worse for some other customers. So it really depends on where you are connected to the network and where this particular coil is connected. Now, one other approach would be to introduce redundancy into the system so that if you have a disturbance, the effect of this disturbance, the effect of this fault on the system would be less. There are a lot of different techniques. We're going to go through some of them in the next couple of slides. Consider this network on the left. Here is a system without redundancy. You have a distribution substation, and then you have your laterals. In this particular case, your feeders and laterals are protected with the fuses. There is no redundancy. If anything happens to this particular distribution substation, everybody is going to be out of service. On the other hand, the system on the right side, that is a system with redundancy because you now have multiple substations that are feeding the load area. Not only that, each substation has more than one distribution transformer. So even if one transformer goes out, the other one can pick up the load. Typically, you know that in North America, distribution systems are in radial format. So when you have these kind of meshed or loop configurations, you have to have switches in between that are normally open. So these are normally open switches, meaning that under normal operating conditions, these are not connected. The system is still a radial network. However, if anything happens, for example, to the substation on the left, you can basically isolate this substation by opening the corresponding breakers and then close this switch so that all the loads here, here, and here will be fed from this other alternative supply. So that's one way to introduce redundancy. Another solution would be the usage of load transfer. These are power electronics-based switches known as static transfer switches that allow loads to switch between a primary source and an alternate source if anything happens to that primary source. Consider the diagram on the left. Here I have two loads. The load on the left is being supplied by the primary source and the load on the right by the alternate source. Now imagine something happens to this primary source and it's going to be out of service. Now here what I can do is by sending the proper gate switches to these SCRs here and here that are back-to-back SCRs, I can connect this load on the left to the alternate source. Because these transfer switches are extremely fast, even they can operate sub-cycle, that means the load is going to be experiencing a very, very short glitch in service. So for majority of appliances and equipment, this is going to be okay. One other thing you notice in this diagram is I have another switch in parallel to those two back-to-back thyristors. This is intentional because once you have made the connection between the load on the left and the alternate source, you basically don't want to keep sending pulses to these SCRs for losses, and in addition to that, because you want to avoid wear and tear. So what you do is as they are open, they are receiving their gate pulses, you go ahead and send a command to this automatic switch, which I'm showing here in blue. Once that one is closed, then you can stop sending gate pulses to the transfer switches because it's not necessary anymore. We do it this way because that automatic switch typically operates within a few cycles, unlike the SCRs that can operate sub-cycle. So for some certain sensitive cases, a few cycle of delay in being connected to the alternate source is not sufficient, which is why we use the SCRs in parallel to those. This scheme was for having two loads that are connected to two different sources, and then they have the capability of being fed from the other source as well. For very, very sensitive loads, we can actually have a single load, which is connected to both a primary and an alternate source. Now, between the load and each of those sources, you're going to have a static transfer switch. During normal operation, this is going to be supplying the load. If there's anything wrong with this supply, then this one is going to be supplying the load. This is one of the most efficient ways of ensuring uninterruptible supply to sensitive loads. There are other ways to improve the redundancy of the system. One of them is to use parallel networks and loop networks. Loop networks will allow you to have multiple paths between a source and a load. Parallel networks allow you to have multiple devices so that if one of them fails, the other ones can take over. For example, here you have a distribution substation with multiple transformers. Here you have not only multiple transformers, but also multiple substations. So by adding to the number of substations, number of normally open tie lines, number of transformers, you can improve the redundancy of the system. This can significantly improve reliability and reduce the number of voltage sags and interruptions, but keep in mind that it's an expensive solution. So you typically do this when the load is very, very critical and sensitive. Now, when we talked about coordination between auto-recloser and fuses for fuse saving purposes, meaning that the auto-recloser at the feeder head will respond to all the faults first before the fuses have a chance to melt their elements, which leads to permanent faults. When we talked about that technique, you remember that one of the disadvantages of this would have been everybody will experience at least a momentary interruption. So it is good in a sense that people, let's say there is a fault on this lateral. With fuse saving, of course, you don't let this fuse to operate first. Your auto-recloser will operate first. So instead of having all the customers connected to that particular lateral to experience a sustained interruption, instead of doing that, what we do is we open the recloser at the feeder head, so everybody will experience a momentary interruption. And then hopefully this fault has been temporary in nature, so by the time you reclose, the fault is gone and everybody is okay. Sometimes, however, this is not desired because sometimes you may have very, very sensitive loads connected to a certain part of the feeder that they don't want to tolerate the slightest amount and the least number of momentary interruptions. So in situations like that, instead of having one recloser at the feeder head, which will disconnect everyone along the main feeder and along all laterals, what we do is we sectionalize the feeder. So here you're going to have one circuit breaker at the feeder head. This may not be a recloser. This may be just like a traditional overcurrent protection relay, which is controlling that circuit breaker. And then somewhere down the feeder, you now add a recloser. So now if there is a fault, instead of this breaker opening up, meaning that everyone along the feeder will experience momentary interruptions, this guy will open. So everybody upstream of that recloser which has been added, everybody who's upstream of that recloser is not going to be experiencing anything rather than a voltage sag. So there's not going to be an interruption. And depending on how long this feeder is, you can actually expand this scheme and you can have multiple reclosers that are sectionalizing a long feeder. You just need to make sure that you have proper coordination between these devices so that the right one will open before the ones that are upstream are activated. The notion of adding reclosers typically is something that we do to the main feeder and not the laterals, but this is not necessary. Sometimes if you have a very, very secure and reliable main feeder, and then you have sub feeders that are feeding off of that main feeder, you can actually add the auto reclosers to those sub feeders, which is what I'm showing in this diagram. So here you have a main feeder, which I'm showing with a slightly thicker line, and this is being controlled by a regular circuit breaker, which is being controlled by an overcurrent protection device. But then the sub feeders are going to be having their own auto reclosers in case we want to implement fuse saving. Okay, let's have a recap of what we've been talking about. So far, we have focused on techniques that allow us to reduce the number of short circuit faults in the system. Then we shifted our focus to the power grid itself, and we looked into solutions to improve the efficiency of the protection system and also reduce the severity and impact of disturbances on the equipment. Now it's time to shift our focus to the customer side. What can customers do? One approach that customers can adopt is to use auxiliary devices, compensating devices that can help them withstand voltage sags and interruptions for a longer period of time and events that are more severe. These are typically used by customers who have loads which are sensitive. Not very common for residential units, but very, very common in industrial units and also some commercial systems. So let's go through some of these solutions. One is known as the DVR, or the Dynamic Voltage Restorer. DVR is essentially a voltage source inverter that can inject a voltage in series with the line. So here you have your source side on the left, and then you have your load on the right. Without this device, if the source voltage goes down, the load is going to be directly experiencing that. However, when you have the DVR, what you can do is you can inject a voltage in series with the system, or as a matter of fact, I should use a different polarity, so plus and minus. So you inject this voltage in series with the line. From the load perspective, the voltage at the load side will be this voltage plus this voltage. So even if the source voltage goes down, you can compensate for it by that series voltage that is injected into the line. The capacity of this DVR will tell you how big of a voltage sag you can compensate for, but the duration of voltage sag that you can compensate for depends on the energy storage that you have. So the size of this energy storage system will tell you for how long you can compensate for a particular voltage sag. So there are two important characteristics. One is the rating of the device itself, which tells you how much maximum voltage it can inject into the line. And second one is the size of the energy storage system, which tells you for what duration of time it can provide that voltage. Another solution which is quite common for sensitive loads is UPS, or uninterruptible power supply. Here we use power electronic circuitry to make sure that the loads are always going to be supplied with some sort of a supply, either the main grid or my backup generation. So there are different configurations for UPS systems. This is one example that I'm showing you here. So notice that I have the connection to the main grid, and there is a bypass line that connects the grid directly to the load. But at the same time, there is a second path. This is the path through the UPS, meaning that the AC voltage here is first rectified to DC. This DC is going to be charging my battery system, and then the battery will be used, or the battery voltage will be used through an inverter to generate an AC voltage. Now, UPS systems operate based on different schemes. One is the standby scheme, in a sense that this system is not operating under normal operating conditions. The only thing that is happening is that the rectifier keeps charging up the battery to account for and compensate for the self-discharge rate of the battery. Otherwise, the inverter is not operating during normal operating condition, and the load is connected directly to the grid. If anything happens, then this switch opens and opens basically the connection to the main grid and connects to this line, meaning that the battery, which is being charged, is now going to be discharged through the inverter into the load. That's a standby technique. There is an online technique as well. This is for very, very sensitive loads that cannot even tolerate loss of voltage or voltage sags for like a fraction of a cycle. In situations like that, you typically don't have that bypass line, and essentially the voltage that is coming from the grid directly is rectified through the rectifier. Rectifier is charging the battery. Battery is the one providing energy to the load through the inverter. So this lower path is operational at all times. This will give you high reliability, of course, but at the expense of higher cost, more wear and tear, and more losses, because the rectifier and inverter have losses internally, and also, as you know, batteries have a cost associated with them, in a sense that when you purchase a battery, it can go through a certain number of deep discharge cycles. So if you keep using it, that means the lifetime of the battery is going to be reduced. But for certain loads, this is a risk we're willing to take because they're very sensitive. Another solution is what we know as motor generator sets. This is kind of the mechanical counterpart of a UPS. So instead of having a rectifier, a battery, and an inverter, what we have is a motor connected to a flywheel connected to a generator. Under normal operating condition, this motor is being supplied by the utility, essentially the generator's rotor is mounted on the shaft of the motor. So as the motor spins, the rotor of the generator spins and is generating electricity. We also add a flywheel there to add to the rotational inertia of the mass connected to that shaft. If anything happens to the grid, let's say the voltage is gone on this side, so no voltage is being supplied to the motor. However, because of the inertia of the flywheel, the generator will continue spinning for a certain period of time, and during that time, it will continue supplying the sensitive load. You do have to keep in mind, though, when the generator is operating on its own, it's basically utilizing its kinetic energy to provide electric energy into the load. This means that as it provides its energy to the load, it starts slowing down, so the frequency of the voltage provided to the load as well as the magnitude of the voltage will go down. So this really can continue for a certain period of time, which depends on how sensitive the loads are. If the load, for example, can tolerate up to 20% of drop in frequency, it can run for a longer period of time. However, if the load can only, let's say, tolerate up to 58 hertz, so that means you can have a shorter period of time where this generator is going to be effective. The moment it slows down beyond, let's say, 58 hertz, then this frequency that it provides for the load is not sufficient anymore, and the load has to disconnect. There are a variety of different configurations for this. So for example, you can make this instead of, so this would be similar to what we talked about on the previous slide. This would be like the online scheme. In addition to that, you can have more like a hybrid scheme or standby scheme, whereas this is not providing the power at all times. Normal operating condition, it could be operating as a synchronous condenser, and then if anything happens, it can start injecting active power. Recently, there have been some changes to improve the performance of these motor generator sets by using adjustable speed drives with the motors and also a rectifier after the generator. The benefit is that by using the adjustable speed drive, you can increase the rotational speed of the motor beyond 60 hertz. What is the benefit of that? The higher the rotational speed, the higher the kinetic energy. So you'll have more kinetic energy to then convert to electricity. On the other hand, what is the benefit of using that AC to DC rectifier in the output? The benefit is you can let the generator run for a longer period of time, because regardless of how much the frequency drops and how much the voltage drops, by using the proper switching of the rectifier, you might be able to still maintain an acceptable level of voltage to the load. So loads might actually be quite sensitive to drop in frequency, but using that rectifier, you're not worried about frequency anymore. You're just worried about getting the right voltage magnitude. So this basically allows you to utilize more of the energy of your device than before. All right, let's go through an activity. So let's say I have a 50 hertz system. So this is a European system. Of course, 50 hertz is not just in Europe. In majority of countries in the world, in Asia, in the Middle East, in Africa, the frequency used is 50 hertz. So let's say we have a 50 hertz system, and with this scheme, we have a motor generator set, and we have a load that is connected to that generator, which is quite sensitive, and it can continue operating until the frequency drops to as low as 45 hertz, which is 10% drop. If the frequency goes below 45, the load has to disconnect because it cannot operate with a lower frequency. What I'd like you to do is to calculate how much of the energy of that rotating mass, the flywheel and the rotors and the shaft, is actually wasted. So how much of it is put to use, how much of it is wasted. Now what we do is, to improve the performance of this system, we notice that if we use a rectifier at the output of the generator, we can continue using that generator to provide constant DC even at 50% of rated speed. Right? And further, if I use an adjustable speed drive as the input of the motor to kind of overspeed the flywheel by 20%, what I would like to know is how much more of the energy of the flywheel these variety of techniques allow me to use. Similar to before, I'd like to ask that you pause the video at this point. Give yourself 5 or 10 minutes, think about this. When you're ready to move on and go through the solution, hit play. Okay, I trust that you worked on this exercise, so let's think about it. If the system can operate, or the load can be supplied by the generator for as long as the frequency is above 45 hertz, that means that it can only tolerate a 10% drop in the generator speed. 10% drop in generator speed, that means that the speed has dropped to 90%. Now remember, what is being delivered to the load, or kind of stored in that device, is that energy of the flywheel. This is the kinetic energy due to the rotation of the mass. If at 90% of the speed I have to disconnect the generator and the flywheel from the load, that means 81% of the energy of the flywheel goes to waste. Why? Because at 90% of rated speed, the kinetic energy of the flywheel is 1/2 of j omega squared. When omega becomes 0.9 times omega, energy becomes 0.81, or 0.9 times 0.9 times the rated energy. That means when you disconnect the load, you still have 81% of that kinetic energy left, and that is the energy that is going to waste. Only 19% is used. Now, in the second scenario, when we use the rectifier, we assume that we can continue operating until the voltage reaches 50%, the speed reaches 50%. If the speed reaches 50%, that means the energy remained in the flywheel is 1/2 of j times 0.5 times rated omega squared. 0.5 times 0.5, that's 0.25. That means 25% of the energy now goes to waste. So unlike the previous case, 75% of the energy is going to be used. And you can follow this logic. If I use an adjustable speed drive to overspeed that flywheel by 20%, that means my omega is going to be 1.2 times omega. That means I will have 144% energy compared to the rated situation. And 144% energy available, I will stop. Remember, I still have the converter, so I will stop when 25% energy is remaining. So 144 minus 25%, that's 119%. So by using that adjustable speed drive and the rectifier, I can utilize 6 times more of the energy of the flywheel compared to the base case. When you use 6 times more energy, that means your ride-through duration through the fault is going to be 6 times longer. Other solutions that end users can utilize would be energy storage systems. There are a variety of different techniques here. We can use batteries, we can use supercapacitors, we can use superconducting coils, we can use flywheels, and the objective of all of these would be to continue supplying the load for a certain period of time. Naturally, for solutions like batteries, for example, you can supply the load for a longer period of time, whereas flywheels, on the other hand, would have a limited write-through capability. But depending on how sensitive your load is, these are some other solutions that you can use. All right, the last category of techniques to help customers that we'll talk about is motor starting. Let's refresh our memory about what we talked about before in terms of the impact of motor starting on voltage sag. So what we saw is that if you have induction motors and you connect them to the grid, when you start them up, the motor, because it's starting from standstill, it's going to be a highly inductive network that will draw a significant amount of current, between 5 to 10 times the rated current. This large inrush current that is drawn by the motor will flow through the system, causing voltage drops, and will create a significant voltage sag for every customer that is connected to that load. So when this motor is directly supplied by the utility, the load here will experience a sag in voltage. We did this analysis in class, that if the locked rotor impedance of this motor is ZLR, using voltage division, I have a voltage of E that drops across ZS and ZLR. Using voltage division, the voltage that the customer at this point of common coupling will experience will be ZLR divided by ZLR plus ZS times E. Oftentimes it's safe to assume that these impedances are mostly reactive, so the resistive portion is small, so you can change it to X of locked rotor divided by X of locked rotor plus the X or reactance of the supply. And then we saw that the locked rotor reactance of an induction motor can be written as the voltage squared divided by the locked rotor power, S of LR, and the ZS, which is the source impedance, can be written as voltage squared divided by the short circuit power. If we do a little bit of mathematical manipulation of this equation, we can see that the voltage that the customer experiences here at that point of common coupling would be the short circuit power divided by short circuit power plus the locked rotor power of the motor. So these have certain conclusions for us. For example, if the system is strong, meaning that short circuit power is large, so the voltage that the customer experiences will be high, which is desired. Or for example, if the locked rotor power of the motor is small, again, we're going to have the same effect. But in a lot of cases, when you start an induction motor by connecting it to the full voltage, you will have a significant inrush current and everybody's going to be affected. Motor starters are a solution that can avoid this particular type of voltage sag. So the objective behind these starting methods is to basically reduce the voltage that is being applied to the motor during startup. When you reduce the voltage applied to the motor, as a result, you will be reducing the inrush current. So inrush current goes down. That means the voltage drop along the system will be lower, so less customers will experience significant voltage sags. You start the motor with lower voltage, and as it gets closer to steady state, you switch to the full voltage mode. There are quite a few techniques for starting of induction motors. One is the usage of autotransformers. So autotransformers, what they do is they are connected between the motor and the utility, and they have tap positions like 50%, 60%, 80%, and they apply a lower voltage to the motor And as the motor gets close to normal operating condition, you move this tap back to the normal state, so the entire full rated voltage will be applied to the motor. This way the inrush current is going to be lower. Sometimes you can have a 3 auto transformers connected to a 3-phase motor. In certain situations, however, to save on the number of auto transformers connected to the motor, you can actually use an open delta configuration, which I'm showing in this diagram. So here, during startup, you open these 2 switches, so the switches that are green, those are open, and the ones in red are closed. So now you will have one auto transformer and then another auto transformer between phases, let's say A and C, and then phase B will be connected directly to phase B of the supply. And then when the motor gets to normal mode and wants to run normally, you open these switches, the green ones, and you close this switch and this switch so that the motor is directly connected to the supply. The one thing you notice probably in this diagram is that with this open delta configuration, the voltages that are applied to the 3 phases of the motor are not the same. So there's a certain level of imbalance in the voltages. And as you know, imbalance could lead to harmonics and I'm sorry, the sequence components, not harmonics, sequence components in the system, which would lead to additional overheating and things like that, which is not desired. So for large motors, if overheating is a significant problem, you may want to make sure that you use a 3-phase auto transformer, unlike this configuration. Another starting technique is the usage of resistances or reactances that are inserted in series with the motor. So between the motor and the supply, you either inject a resistance or a reactor, and once the motor gets close to normal operating condition, you take them out, you short them out. This, of course, in the resistive solution could lead to losses, but again, this is a short period of time. And the benefit of this would be, again, to reduce the voltage applied to the motor. Yet another technique is part winding starting. This is for motors that have 2 separate windings, stator windings that are in parallel to one another. So these are motors that operate typically for 2 different voltage levels. And for start, what you can do is you can open one set of windings and only supply voltages to one set. So this way the voltage applied to the motor would be less, and hence the current is going to be less. Once the motor runs at normal mode, you close the second batch of windings as well, and then the motor is going to be running in an optimal fashion. And the last technique for motor starting is this. Actually, it says part winding, but it should say Y delta configuration. That's a typo. So in Y delta configuration, what we do is imagine you have a motor that under normal operating condition is connected to the grid through a delta configuration. What we can do is we can connect the motor in Y during startup so that a lower voltage is applied to the windings, and as the motor gets to normal mode, we switch to delta configuration, so a larger voltage will be applied to the windings. You have to keep in mind, however, this is only applicable to motors in which you have access to all the 6 terminals of the stator windings. This is the only type of motor that can operate based on this. So in order to start, notice that the green breakers on the left, these are open. The red switches are closed. So here you have this connection to here, and then here, and then here. So this would be like a Y configuration. When the motor wants to run normally, you make a switch from Y to delta. So you open these switches and close this switch, and this switch, and then you will have your delta configuration. During that time, when you make the transition from Y to delta, you will have some transients. In certain cases, if these transients are significant, then the starting circuit will have some damping resistors to make sure that it can damp out some of those transients. So these are the different techniques that are being used for starting induction motors. And as I mentioned, I should make a correction here that this is a Y delta starting technique. And finally, as we talked about, the ways to reduce the number of short circuits in the system, making the grid more resilient, and having compensating devices or starting techniques for the loads, the final category would be the actual equipment itself. One mitigation technique, of course, would be to make those equipment and appliances more immune. This could be by adding a more efficient and robust power electronic circuitry or drive system for motor loads, or for example, adding capacitors to the internal circuit of the load so that it can maintain constant voltages for a longer period of time. This essentially, the objective here is to allow the device to have less vulnerability to reduction in voltage and the duration of reduction in voltage. So this brings us to the end of this lecture on mitigation techniques for sags and interruptions. These are a series of references that I used throughout this lecture. These are very good books, and I encourage you, if you're interested in knowing more about the techniques we talked about, I encourage you to refer to these references.